So I've already discussed electric potential and capacitance as part of Chapter 17. In this segment, I'll move on to look at current and resistance. We've learned about electric charge previously, but this charge is most useful when we can control its movement through a material. So for this we use electric current, which is defined as the rate at which electric charge passes through a given material. So to write this mathematically, we have I, which is the current, equals delta Q, which is the amount of charge passing through, divided by delta T, which is the time interval in which this transfer occurs. The units for electric currents are A, or amperes, which equal 1 coulomb per second. As electric current moves through a substance, it often meets resistance, which is the opposition that that specific material presents to the electric current moving through it. So we write that resistance is equal to delta V, or potential difference, divided by current. So it's the ratio of potential difference to current. For resistance, the units are ohms, or omega, this Greek letter I've shown here, and 1 ohm is equal to 1 volt per ampere. So knowing that resistance is equal to delta V divided by I, we can multiply this I, or electric current, to the other side to get this equation, delta V equals IR. This is the foundation for Ohm's Law, which states that resistance is somewhat constant over a wide range of potential differences in materials that are said to be ohmic. So essentially that just describes how current flows through a material and the resistance that's present. When we're looking at resistant materials, there are a few factors that affect just how resistant they are. The first is the length of the material. As length increases, so does resistance. There will be more resistance in a longer material. The second factor is cross-sectional area. This is inversely related to resistance, so as the cross-sectional area becomes smaller, resistance will become bigger. The third is material. This is sort of impossible to quantify, but certain materials are more resistant to electric current than others. Finally, we have temperature, which is also directly related to resistance. So as the temperature becomes higher, resistance will become greater. So these resisting factors are important because they can be used to control the amount of current in a conductor. Now for some practice problems. Number 1. If the current of a wire of a CD player is 0.005 amperes, how long would it take for 2 coulombs of charge to pass through a cross-sectional area of the wire? So essentially we'll be using this equation for current, where I is the ratio of delta Q over delta T. We know that the current is 0.005 because that's from the problem statement. Then the change in charge, or delta Q, is equal to 2 coulombs because that's how much passes through. And then finally we're solving for T. So if I multiply T over to the left side, I get 0.005 T equals 2. By dividing both sides by 0.005 to isolate T, I find that the time it would take is 400 seconds. Number 2. The compressor on an air conditioner draws 40 amps when it starts up. If the startup time is 0.5 seconds, how much charge passes through a cross-sectional area of the circuit in this time? So we're using the equation again, I equals delta Q divided by delta T. We know that the current is 40, and this time we're solving for delta Q, which is how much charge passes through a cross-sectional area. And then finally we know that the startup time is 0.5 seconds, so we plug in the 0.5. To isolate delta Q, we would multiply the 0.5 over to the other side to get that the charge that passes through equals 20 coulombs. Number 3. A 1.5 volt battery is connected to a light bulb with a resistance of 3.5 ohms. What is the current in the bulb? So this time we're using Ohm's Law, where the volts are equal to current times resistance, or V equals IR. So we know that it's 1.5 volts, so we plug that in on the left. The resistance is 3.5 ohms, so that's this R, and then we'll be multiplying by I, which is what we're solving for because that's the current. So to do so, we will divide both sides by 3.5 to get that I equals 0.43 amperes. Number 4. An ammeter registers 2.5 amps of current in a wire that is connected to a 9-volt battery. What is the wire's resistance? So again, we're going back to this V equals IR. This time we know that the voltage is 9, we know that the current is 2.5 amps, and we're multiplying by R, which is what we're solving for. That's the resistance. So to find R, we'll divide both sides by 2.5 and get that R is equal to about 3.6 ohms, which I should really write as omega.